area of a surface of revolution. Now here I have 4 different formulas here, and each of these can be used in different ways. Well, depending on the situation, it's one of these formulas is the one that you're going to use. Okay, so let's just take a look at a few different situations that you could be faced with. So let's suppose that you had a surface, like you had a curve like that, and let's say that you were evolving this about the x-axis, okay, just as an example. Okay, and let's say that we had y equals f of x was the equation, okay? Then, okay, what would happen is you would get something like this. Wait, that's right. You get something like this, okay? You get some object like this. Okay, so that's what your rotations would be like. Okay, now you want to know what the surface is. Okay, so this outside. So maybe this looks kind of like a bell, eh? So maybe, okay, so what's the surface area of the bell? Let's say we wanted to paint the bell, for example. What's the surface area of that bell? Well, we're looking at, like, if you have a circle and you're looking at the surface area, then, and let's say that it's like a little tiny cylinder. So the area of a cylinder is 2 pi r h, right? Okay, now the h in this case is going to be the distance this way. Okay, so in this case it's going to be dx. Okay, so that's the height. Now, if we were rotating it, yes, so this, in this case, if you take a cylinder like this, then the height of that cylinder is going to be dx in the x direction. Okay, and the radius is going to be f of x in this case. And so what we would do is we would use this first formula for this situation. And this y here would be replaced with f of x, would be replaced with this. Okay, so this f of x would go right into there, and then you have the dx, okay? And then dy dx would be, you take the derivative with respect to x, and that would be dy dx. Okay, so that's this situation here. Now, just going to go through another situation that you might have. Now, it's there's also this formula right here that also has a dx, but then this is not right. This is an x right here. Okay, so there's different formulas. So if you had, here's another situation. Let's suppose that you had you're still rotating about the x-axis, but let's say that this right here was x equals g of y instead. Okay, let's say that's the formula right there. X equals g of y. Okay, then so you're rotating here. Trying to like draw the reflection here. Okay, so you're rotating here. Now, if you take one of these discs right here, just take a split slice out here, so you have this disc. Then the thickness of the disc let's see, what's the radius? The radius is going to be so when you go 2 pi r h, Okay, let's see, what's the radius? It'll be this distance from here all the way up to here. Okay. And that, this time, the radius is going to be y. Okay, it's still the same y there. However, when you're looking at the height would be this, like here. Dang, I can't believe I'm confused here. The thing is that when you're going for dx dy, you're going to have to use this formula here. You'll have to take the derivative of x with respect to y for this lot. And the y, dang, this was so clear to me before. Now you're just going to use a plain old y here. You're just going to use a y as the variable. You're not going to use an f of x. You're just going to use y. And instead of, okay, so here you're integrating from a to b, but instead here you're going to be integrating from c to d. And you're just going to use a straight up dy right there. Okay. So that's kind of how things go. And then these two formulas here are for when you're rotating about the y-axis. Okay. These two different formulas here, depending on whether you have y equals something or you have x equals something. Okay. So that's how things work. So let's go ahead and do some exercises. And so the first one, we have x equals something. X equals y plus y cubed from 0 to 1. Okay, and here you're evolving it around the x-axis. Okay, so that is pretty much, that's actually the second case where we have x equals, so basically x equals g of y, and then the second case. And so when you're evolving it about the x-axis, you just put we're going to be using, let me go back. We're going to be using this formula here. So this is just 2 pi y. Okay. So 2 pi y, this goes there. And then the square root of 1 plus, okay, then we take dx dy is, just take the derivative with respect to y. So that's 1 plus 3y squared. Okay, so that's 1 plus 3y squared quantity squared. Okay, that goes right there, and that's it. So that's what that's going to be. That's going to be the answer to the first one. Okay, so notice that I took the derivative with respect to y, I treated x as the dependent variable in this case, and just calculated that. Okay. Now the reason that you have a dy here is it's just because of this formula here, the way that it is. Really, kind of what you sort of have to start out with is you got this. This is your arc length right here, really. And so you can either this is equivalent to this one, or this one. We can sort of see that it's equivalent to either of those. So here, if you take this dx and distribute it inside, it goes in as a dx squared, and you're going to get this because the dx squared here is going to cancel. If you take this dy and put it inside, then it goes into dy squared, and you're just going to get this either way. Okay, so there's two ways you can go, that or that. Okay, now in this case, we're going to be, in the second case, we're going to be rotating about the y-axis. Okay, so when you're rotating about the y-axis, then again, we're still going to use this dx dy equals 1 plus 3y squared. But what we're going to be doing is this. So it's going to be this formula here. Okay, this formula here. So we're using this one. And so we have the dx dy here, which means we're going to have an x right here, a dy there, and this is x. So, but x is equal to y plus y cubed. So it's actually 2 pi, and the x gets replaced with y plus y cubed because you have to have everything in y's. And the square root of 1 plus 3y squared, and then dy, like that. Okay, that's rotating about the y-axis. So that is this case right here that we're looking at. Okay, now numerical integration capability of a calculator to evaluate the surface area is correct to 4 decimal places. So we're going to be putting these integrals in to a calculator. So let me show you how you can do that. And last time I showed you Wolfram Alpha, but this time I'm going to use Geogebra. I think it's geogebra.org. Okay, so let's see. Let's go. So let's flip over to Geogebra. Okay, so geogebra.org. And I'm going to, let's see here. I think any calculator would be okay. I'm not sure if there's any difference between these, but I'm going to choose CAS calculator. I think any calculator can do it. Okay, so when you go, if you start typing in the word integral, then it gives you these different options. And so I'm going to put integral in, and I'm going to choose this option here. So the function that I'm going to put in is the first one. I'm going to go 2 pi. I'm going to go times pi times, instead of y's, I'm going to put x's because I think they want you to have, I'm not sure if you put a y there, if that would work or not. Okay, so times this, and then square root which is that one. I'll click that one. The square root of 1 plus, and then we have 1 plus 3x squared. Okay, and then the next thing that they want you to do is the beginning value. Oh, come on, man. Okay, let me give myself some more space here. There we go. Okay, so the start value, I'm going to make that 0, and the end value is 1. There we go. Okay, so then hit enter. And it gives you this thing right here. If you click this little like wavy lines here, then it gives you the approximate, which is 8.5302. They said 4 decimal places, so 8.5302. Okay, and now it looks like our integral there. Okay, so then we'll do the next one, integrate. And I'll just write it out this time. So 2 times pi times the square root, times x plus x cubed. I'm changing the x's to, I mean the y's to x's, by the way. Square root of 1 and that goes from, also goes from 0 to 1. Okay, I made a mistake somewhere. Whoa. Oh, I think it was integral. Yeah, integral. Boo. Okay, I guess that they want to be really mean today. Copy, paste. There we go. What the? Okay, and then there's that integral right there. Oh, it looks pretty nasty. I forgot a 2 there. Okay. 13.5134. 13.5134. Okay. So those are the answers that we got. Again, which was for the first one when we rounded off, it's 8.5302, and the second one, 13.5134. Okay. Okay. Any questions about any of that? Okay, let's go on to the next one. Hopefully some more interesting adventures here. Okay, so number 2, find the exact area of the surface obtained by rotating the curve about the x-axis. Okay, so there's this curve here that we're rotating about the x-axis. So that means, because we're rotating about the x-axis, that means it's going to be the integral from 0 to 2. These are values in x, dx. And what do we have? 2 pi y times the square root of 1 plus dy dx squared. Okay, because this is y in terms of x, so this will be dx, and then that. And so let's just start plugging things in. Our y is going to be this, the square root of 1 plus e to the x. That's our y. Okay, now we need to figure out what dy dx is and square it. So let's do that really quickly. I like to write it as e to the 1 plus e to the x to the 1/2 instead of writing the square root. And that's a 1/2, not a y2. Okay, so dy dx, we'll take the derivative of this. Okay, so first of all, the 1/2 comes down in front. And then this is reduced by 1 by 1. So 1/2 minus 1 is negative 1/2. Okay, and then multiply by the derivative of the inside part, which is just e to the x. Okay, so then dy dx squared is going to be, well, let me do one more step, okay? One more step before I do that. This is going to be e to the x over 2 times the square root of 1 plus e to the x. Okay, so I'm just putting this down as the square root of 1 plus x. So now when I square it, I get e to the 2x over 4 times 1 plus e to the x. Okay, so that's what I put in here. That's weird. And then on the end we have a dx. Okay, now what I'm going to do is we have a square root of something times the square root of something else. So it's the square root of the product of the insides, okay? So 1 big square root. Now I'm going to take, so they basically just take this and multiply by 1 plus, and then multiply this by this, but then when I multiply this with this, then the 1 plus e to the x is cancel. So I have e to the 2x over 4. That looks really suspicious. Yes, okay, I see what that is. That is e to the 2x over 4 is really e to the x over 2 squared, okay? Oh, going from 0 to 2. But that's just e to the x over 2 plus 1 squared. Okay, so you have something squared and then the square root. Those got two operations, cancel each other out. So we just have that, which is, okay, distributed the 2 in. I'll take the pi out. So you have e to the x plus 2. Oh, interesting. Okay, integrate. That's e to the x plus 2x, going from 0 to 2. And let's see, we get e squared plus, if we put 2 in there, you get 4, and then subtract e to the 0, and then 0. So it's going to be e squared plus 3, because that's 1. That's 1. Okay, so that's going to be the answer right there. Just because this piece is, that's 1. So it's 4 minus 1. So 4 minus 1 is 3. There you go. Okay, any questions about that one? Okay, so that was that's like the first case. Let's do number 3. Find the exact area of the curve obtained by rotating the curve about the area of the surface by rotating the curve about the x-axis. Okay, so this one is x equals something, but rotated about the x-axis. Okay, so you're integrating on y, and y is going from 1 to 2. So that's going to be dy there. And you have 1 plus, and then this is in terms of y also. So you got dx dy squared, and then 2 pi wait a second, what is this? Two pi y right there. Because when you rotate about the x-axis, then when you're rotating about the x-axis, so here's the x-axis, rotating about that, then your radius is always going to be y. But it's whether you just leave it as a y or whether you have y equals some function in x. Okay, so since we're integrating in y and dy, then we're just going to leave that as a y because we already have everything else is in terms of y. The only thing that changes would be this right here. So dx dy, okay, integrate this with respect to y, that's 0. And then derivative, I mean, not integrate, differentiate this. And then this is, the derivative of this is 4y. Okay, so that's 4y. So dx dy squared is going to be 16y squared. Okay, so that becomes 16y squared right there. Okay, now for a second I was thinking, oh no, do I have to do some trig substitution? But then I saw if you take the derivative of this part, of this, you get, what is it, 32y? But there's a y right there, so we're good. You can just go ahead and integrate this. Okay, so if I raise this by 1 power, I get 3 halves. Okay, now, and I have a 2 pi. Now, if I take the derivative of this, I'll get a 3 halves coming down. So to counter that, I'm going to put 2/3 right there. Okay, so when this 3 halves comes down, this 2/3 will cancel it out. Okay, then this reduces by 1 power, so 3 halves minus 1 is 1 half. And then then I have to multiply the derivative inside. The derivative of this part inside is 0 plus 32y. There's the y, but we have no 32 to counter it, so I'll put 1 over 32 right there. And of course, this goes from 1 to 2. Okay, now I have a 2 here and a 2 there, and that's going to be 8. So it's going to be pi over, this reduces the power over 24, okay? Because 32 divided by 4 is 8. 8 times 3 is 24. So yeah, pi over 24 on the outside like that. Okay, now if I put a 2 in, I have, let's see, 1 plus, what was it, 2 times 16 is, no, 2 squared is 4. 4 times 16 is 64. So that's 1 plus 64 to the 3 halves minus, and I put a 1 in, I get 2 to the 3 halves. Okay, now when you have something that's to the 3 halves, you can write it as, so this is 65 to the 3 halves, so you can write it as 65 times the square root of 65, and then this 2 can be written as 2 times the square root of 2. Okay, because like, I'll just kind of show you here. 3 is like 2 to the 1 times 2 to the 1/2. Because 1 and 1/2 adds up to 3 halves. So that's 2 root 2. Wait a minute. I made a mistake. I made a terrible mistake. This is not, okay, so this is not 1 plus 1, it's 1 plus 16, which is 17. So it's 17 root 17 right there. Okay, any questions about that one? Okay, we'll move on to number 4. And finally, we get something rotated about the y-axis. Okay, we're rotating about the y-axis. And we have this right here. We have y equals, and we're integrating in x. Okay, so if we're rotating about the y-axis, okay, so these, so let me just make a note right here. These formulas here are for rotating about the y-axis. Okay, and these formulas are for rotating about the x-axis. Okay, so here we're rotating about the y-axis. And so the way you look at it is if you're rotating about the x-axis, then you're using this one. And then you're using one of those two. And then the way that you figure out which one it is do you have y equals f of x, or do you have x equals g of y? Okay, and that should be pretty straightforward to figure. So if you have, and the same thing here. So if you have y equals f of x, then you're calculating dy dx. If you have x equals g of y, then you're calculating dx dy. Okay, and another thing, the way that you can tell it's about the x-axis is because about the y-axis. I'm sorry. The way you can tell it about the y-axis is that your radius is x. Okay, so if you're rotating, so like if you're rotating about the x-axis, then your radius is always y. And about the y-axis, then your radius is always x. Okay. Okay, so your surface area is going to be the integral. We're going from 1 to 5 because we're integrating y. So that means it's the dx on the end here. 2 pi, and since we're rotating about the y-axis, our radius is x. And we don't have to, since we're integrating in x, then we don't have to change it. Okay, and then we got that, dy dx squared. Okay, so let's see here. Let's calculate dy dx first. So 2 comes down and makes it 1/2. So we have 1/2 x minus, and then the derivative of this is the derivative of log is 1 over x. So that's 1 over 2x. And let's see, if you square that, I guess we could rewrite it as 1/2 and then have it be x minus 1 over x. Yeah, that's probably better. Okay, so this is going to be, so now it's just squaring this right here. So that's 1/4. Okay, then you have the first one squared minus, well, plus, which is going to be a minus because the product of these two times 2. But the product of those two is just, they cancel each other out when you multiply them together. You just get -1. So it's -2. And then plus the second one squared, which is 1/x squared, like that. Okay. So I'm going to plug this in here for this. So 1/, so 2 pi x times the square root of, now 1 is the same as 4/4. I'm going to write it as 4/4 because I have a 1/4 right here. So okay, so there's that right there, dx. Okay, now if I put this in, if I take this 4 inside, because this is divided by 4, that's also divided, all this is also divided by 4. So I can just put, let's say 4 minus 2 is +2. Okay, so I've got 1/4, and then I have x squared plus 2 plus 1/x squared. Okay, and then I look at this right here. When I squared this, I got that. But now I just have a +2 instead of a -2. So wait, what am I doing? So it's just going to be 1 plus 1/x squared is what all this is. And I can apply the square root to that, apply the square root to this, I get 1/2. That becomes 1/2. And then apply the square root to this part, and I just get x plus 1/x. Okay, so now this is really great. So these 2's cancel. And I can distribute the x in, so I get x squared plus 1. Okay, so x times x is x squared, x times 1/x is 1. And just integrate. So the integral of x squared is x cubed over 3, and the integral of 1 is just x. And I'm evaluating that from 1 to 5. So I get 5 cubed over 3 plus 5 minus, that's plugging 5's in here and here. And then plugging 1's in here, I get 1/3 plus 1. And if I use a calculator to evaluate this, I get 136 pi over 3. Let's see, is that correct? That's 125 there, and this is 15, so that's 140. And then I'm subtracting 1, so that's 139, and I'm subtracting another 3, so that's 136. Yeah, 136 pi over 3. Okay, any questions about that?
Yeah, could you explain one more time what happened to the 4/4 plus the 1/4 in
The 4 right here?
Yeah.
The 4/4? Okay, so that went, so this, what happened there was